Welcome back, everybody. This is AP Chemistry. We're in Unit 7, and this is Section 2. Taking a look again at equilibrium, and we're going to be evaluating the value of Q, how likely it is to go, and which direction it's going to go now. This is going to be the change that we've had in the from the previous section. Previous section, we could tell which direction a reaction is going to be going quite simply. So let's do a quick review of that piece. Equilibrium expressions do involve concentrations or pressures, as we saw in the last problem, that only involve substances that change from initial to equilibrium conditions. Remember that pure substances, a liquid or a solid, really change the amount, but never the concentration. And so if I was going to take a look at these three types of examples, if I was going to write an equilibrium expression for there, here's where those states of matter really play a factor. Remember, they don't affect the concentration of anything along the way. So my equilibrium expression is still going to be a function of that K value, the concentration constant here. But notice that this is a solid, this is a solid. So really, if I'm going to be taking a look at this, I know the product side, I have calcium oxide times my carbon dioxide, and they're both to the 1 power, and that will be over my calcium carbonate, and that's going to be a solid to the 1 power. But since these are solids, I wouldn't even include that, so my Kc would literally be just my concentration of gas at the end. Same thing would be holding true for this solid and this liquid, so my Kc value would then be at the end of equilibrium, just my chlorine gas. And notice that this is also one solid and this is one solid, so my K value would just be my water, which we tend to think of as a liquid, but they did express this as a gas here, so my water would then be the concentration. But watch out, because it is raised to the 5th power. So I can figure out those things several different ways. Now, with having said that, we can take a look at one other thing, because equilibrium does tell us how far it's going to go, how much of the reactants are going to be involved in there. Remember that if I have a large Kc or a small Kc, that's going to tell me, and really when I mean large and small, notice that the number is basically 1. If I have mostly products or mostly reactants, we had to calculate a little bit with our ice chart on how much it went. But it also is used, equilibrium tells me which direction it's going to be used. So if the concentrations are not 0, sometimes we have to figure out which direction it's going to be going. And so I have to establish my Q value, which is related to K. But if they're the same, there is no shift. What we're looking at, the system is already there. If I see that my Q ends up being larger than K, it's going to be making more reactants. And if my Q is less than K, I'm going to be making more of my products. So again, it tells us the key word here is going to be shifting. Which direction is that equilibrium going to be going, or maybe is it in equilibrium already? So given this particular reaction, I'm given some different values here. Notice I've got 3 different experiments, 3 different values in here, but I don't know which direction things are going to be going. Okay, I want to know which direction is it going in each of these trials. Okay, so again, we're going to use our ice charts with it, and we're going to break it down by 3 separate trials here. So again, my K value ends up being, this expression is my ammonia. I use this example a lot just because we have different coefficients in there. That's going to be my nitrogen times my hydrogen. And remember, that's to the 3rd power, my hydrogen's to the 1st power. Okay, let's plug in some values. Now notice on my ice charts, I've got a couple different things going. And we're taking, well, I guess I don't even need an ice chart in this case, because I'm just saying which direction is it going to go. So I want to find which direction based on Q. So in number 1, my Q is going to end up being 0.001 squared divided by my 0.00001 to the 1st power times my 0.002 to the 3rd power. Okay, my Q value ends up then being 1.3 times 10 to the negative 7. Okay, now how does that compare to my K value? Okay, well, my K value was 0.006. So this guy's a lot smaller. My Q ends up being less than my K. So which direction is this reaction going? it's going toward my reactants. In experiment number 2, I have my Q value. I'm plugging in the values. I have a 0.002. Okay, that's my ammonia, and that's going to be raised to the, got rid of that, to the squared. And this is to the second power. And my second value is going to be a 1.5 times 10 to the negative fifth. That's the first power. And a 0.354 that's going to be cubed. So I end up doing the math there. I end up with a 0.06. So here, my Q equals my K. So it's already in equilibrium. Well, I'm just asking which direction is it going. So I don't have to do any other calculations. And so I just know that they are already there. It's at equilibrium already. And so these are my values at the very end. It's done. It's already gone to that point. Now, in experiment number 3, my Q value, again, ends up being a 0.0001 squared divided by my 0.5 to the first power times my 0.01 cubed. And so I end up with a value of 0.002. Well, remember that I had a 0.06 to begin with. So here, my Q value actually ends up being, and I'm sorry, I put this wrong. I'm just realizing that now. My Q value is larger than my, and this was a positive 7. That's where my math was off. I'm sorry. So that's why it's products there, our reactants. And here I see that my Q is now less than my K value. And so then I know that my reaction is going to be shifted and favoring toward the products. Sorry for screwing that up, but you get the idea based with the math on that one. Just predicting the reaction and direction that it's going to be going. Now, here's the main point. I'm not going to reshoot the video just because that silly little thing. Here's the main point. When we're given a scenario like this, okay, we want to calculate the concentration of all the species. If all the species were in there and 3 moles of the product are added to a 1.5 liter container, I want to know the concentration of things when all is said and done. Okay, now this gets a little bit tricky because we got a whole lot of mechanisms here. And notice I've got different values all along the way. The reason I know that is because I see reactants as well as products. We started with 3 moles here, but remember we're in a 1.5 liter container. So I'm going to have to divide that by 1.5, aren't I? So really what I'm starting with in this case of hydrogen is 2 molar solution. Same thing was going on here. 3 divided by my 1.5 liters. I'm going to end up with 2.0 molar solution now. Okay. And lastly, I take a look at my hydrofluoric, and I ended up with 3 moles of hydrofluoric of product. And so that ends up being a 2 molar solution as well. Okay. So in other words, let's put out our ice chart, because we don't know at reaction. The first problem is just asking which direction is it going to be going. But in this case, we know we're starting with all of this. Now, it's not at equilibrium yet. It's going to be reacting and it's going to be doing something. But the question is, what's it going to be doing? Is it going to be taking these two things, making a product? Is the product going to be breaking down because we may have too much to start with? What is going to be going on with this? And so the question is, which direction first? The reason I need to know that question is because I don't know the direction of the change. Is this guy going to be losing something, or are these two going to be losing something? So I need to find that first. So my Q is going to equal my product side. So that's going to be my 2, but that 2 is from my hydrofluoric, so it's going to be squared, divided by my 2 from my hydrogen. Notice there's only one of those, times my 2 from my fluorine, and there is only one of those. Okay, so essentially it's going to be 2 squared divided by 2 squared. So Q ends up being 1, doesn't it? Well, what is K? K is 115. So this tells me, and I won't screw this part up, Q is definitely less than K. So which direction does it go? The reaction is going to the right. It's going to be favoring the products. Now that we know this, Now I can say, okay, there's a multiplier of 1 out here, so I'm going to lose an X amount. I'm going to lose X on this side. This one's also a 1, so I'm going to be losing the same amount on this side. This guy's going to be gaining, but he's going to be gaining twice that. Not because this is 1 and this is 1, but because the coefficient is a 2 here. All right, so let's take a look at equilibrium, what we have. 2 minus my X is going to be 2 minus X. 2 minus X is 2 minus X. And 2 plus 2X, that ends up being a 2 plus 2X. Okay, not rocket science. Now, when we consolidate all this together, I find that my Kc value is 115. That's going to equal my product side, which is 2 plus 2x. It's going to be squared over my 2 minus x to the first power times 2 minus x to the first power. Now, this is a large case, so I can't just simply eliminate those. I do have to distribute this, okay? But this particular problem has an added benefit to it, because if I take a look at this, 2 minus x times 2 minus x, well, that's this. 115 equals 2 plus 2x squared. Well, isn't 2 minus x times 2 minus x, isn't that also 2 minus x squared? So notice this is squared, this is squared. What if I took the square root of everything? Cool, cool, cool math. So I end up with, if I take the square root of 115, I end up with 10.7. That will equal 2 plus 2x over 2 minus x. The reason I say that's cool math is because this is very simple algebra. Let's multiply both sides by 2 minus x, and we'll get the 2x plus 2 plus 2x by itself. I end up with 21.4 minus 10x, and that will equal 2 plus 2x. Now let's combine like terms. 19.4 equals 12.7x. X will then equal 1.53. Okay? So I just divided both sides by 12.7, didn't I? Now, that's not my answer. That's just my x value. So H is 2 minus 1.53. And so 2 minus 1.53 ends up being 0.47 molar. Okay? 2 minus 1.53 is a 0.47 molar. Now, my HF, hydrofluoric acid, that is a 2 plus 2x. So 2 times 1.53, and that will then add 2 to that. I'll end up with a value of 5.06 molar. Okay, so that's my values at the end of equilibrium. And I could get away with some easy math because this ended up, I just was able to take the square root of everything. I think you know what's coming up within section 3. What if you can't? And so then we're going to get into the quadratic formula. But guess what? That's for another time. This one is done. Quite simple, taking a look at how to use your ice charts. And in this case, we're taking a look specifically at how to determine which direction so it could figure out the direction of change. You guys should have enough to go.